So let's start. So I'm the one of the TA of this course, and this is the first time I teach a tutorial in this class. Actually, for today, I will take a look at the problems in week 2 problem set. But actually, some of them are already covered in the lectures by Amir. So for those problems that are covered, I'll direct you and refer the contents of those problems to the lecture notes, and then also of Amir's video. And I'll take a look and I'll go through with you for all those problems that are not covered. So there are several problems that are not covered. And also, for problem 1, I think they don't have a program for it. So I'll also give you the program. So let's start. Yes. So Xuran and I are playing a game similar to Nim. So for this game, there are two numbers, A and B, and each time, each of us, for example, Xuran or I, will decrease one of the number A or B to a number by a non-zero natural value. And you should also know that a player who cannot move in his turns wins the game. So if Xuran decrease the value to A and B to 0, then I'll win the game since I cannot move. And so before we get into the formal proof of this problem, so let's first make some simple observations of this problem. So you can see that since, sorry, is anyone speaking? Okay, so if you have any question, you can just raise them immediately. So for A and B, every time we are decreasing the values of either A or B, so at one point, since A and B must decrease, so at one point, this game will terminate, right? Since we are always decreasing the value, then at some point, A will become 0 and B will become 0. So this is the first observation we can make. And then since this game is deterministic, of course, there's only one winner. Since this game is deterministic means that so we always have only one winner. So for each game state, we always have one winner. And so let's take a look of an example. I'll let G, A, B be the game state. Be the game state that be the winner of this game state when for this value. So let's take a look. So for example, the easiest case is G00. So when A is 0 and B is 0, who is gonna win? So of course, Xuran wins since he cannot move even at the beginning. So Xuran wins. And for G, let's take a look at another example. For example, G01. Since Xuran moves first, so he can only decrease the value he cannot decrease the value by 0 since we have to decrease it by a non-zero natural value. So he must decrease B by 1 so that the game state becomes 0, 0. And then I cannot move. So Zhaorun cannot move and Zhaorun will win. So Zhaorun wins for this game state. And since actually, let's generalize it for any value of B, the game state. You can think of, for example, any value greater than 1. For example, just take B. Xuran moves first. Since we all played optimally, so we are like indefinitely smart, so we can play optimally and we don't make any mistake. So Xuran can figure out an optimal strategy to win in this case. So you can think of B, since we have a value of B greater than 1, then of course Xuran can decrease the value of B to 1. And then from the game state of 0 and 1, I must decrease the value furthermore of 1 so that the game state becomes 0, 0. And then Xuran cannot move, so Xuran will win. And this is the optimal strategy in this case. So Xuran wins. And also same as A0, like they're the same. And another case is, for example, 1. One of the value is 1. Then, of course, Xuran can just decrease the value of A to 0. And then it's the same case as I explained before. So also Xuran wins. Yeah. So these are the observations that we have so far. And also, for each game state, there is only one winner. So if you think of it, if Xuran wins in a particular game state, then for any value of A and B greater than, maybe let me write it. This game state, I win. So if you think of it, for this game state A and B, I win. Then if there's any other game states that are of higher value of A prime and B prime, then if I can reduce it to this AB, this game state, then actually I'll win again, since for this GAB, Xuran starts first, and then it ends up with for me winning. Then if I can reduce it from the higher value to this game state again, then Xuran will also start first. So it's the same case as if Xuran is starting from this GAB. So Xuran will start again from GAB, and then it will end it up with me winning, since we all play optimally and don't make any mistakes. So it will end up with the same results. So this is the observation. So we can actually start like analyze this question. So G00 is X as we have seen it. Xuran, I'll say X is Xuran and Z is Zhaorun. So 01 is Z. So there's another 1, 1. 1, 1, so Xuran starts first. You can decrease the value to 0, one of the A and B to 0, and then I'll have to decrease another to 0. So Xuran will win. And then G20, Xuran will also win, since he can decrease the value to... is there any question? Okay, so he can decrease the value, for example, to this state. since to this state in G01 when oh no, not this state actually just Xuran can decrease the value to 1 0, and then from 1 0 I have to decrease another 1, so it makes 0 0, so Xuran wins. And let me write to actually to 3. So 2 1 is Xuran, G 2 2 is I will win, since so if Xuran, so let's take a look at here. So Xuran can decrease the value. Xuran will always try to decrease the value to a game state that I am already winning. Since so he will try to decrease it to here. So let's see if we can have a way to decrease to a game state of 0 1. So if he decreases A to A by 1, then I'll decrease B by 1. So I'll try to decrease to here, and it will end. So all the possible combination of move will all end up with me winning. So G2 is actually Zhaorun will win. And then let me write to 3, finish the example of 3, and then we're done for this analysis. So these are actually all Xuran wins. But for 3-3, I'll again win. So you can see the patterns here that Xuran wins for all those cases that A is not equal to B. For A is not equal to B, Xuran will always win, since he can always decrease the value to so for all those cases that A is not equal to B, Xuran will win. But for all those cases that A equal to B, Zhaorun will win. So this is the observations that we made, and we will try to use an induction to prove this. Yeah, induction to prove this. So induction step. And for the base case, we have, so we'll just take any base case. We are trying to prove that, for, actually, let me write it here. Prove that when, so let's take, for example, this state, this as our base case. For this base case, when for G21, Xuran can decreases A equals to 2 to A equals to 0. Zhaorun can only decrease B to 0, and then Xuran wins. So this case is true. And the induction step, so we are trying to prove that for all A prime plus B prime, so we have an induction hypothesis. So we assume that we're trying to use strong induction in this step. So we assume that for all A, the sum, A prime plus B prime, when they're all smaller than or equal to A plus B, where at least one of A and B and B is larger then or equal to 2. So for these cases, Xuan wins. This is our hypothesis. And so let's prove that for the game states A, B is the same. So maybe let's use strictly smaller than A plus B. So prove that AB is the same. So let's see. So for the game states GAB, Xuan can always decrease the larger value of A and B. So max A and B to the smaller one. So he can essentially make A and B equal. So decrease one of the larger value to the smaller value. So A and B becomes equal. And then Zhaorun can only make them different, right? Makes A and B different. So this means that A is not equal to B. So as we know that since when A and B is larger than or equal to 2, and A is not equal to B, Xuan will win. So we essentially prove that this is the case for A and B. Since so by induction hypothesis, Xuan will win since Xuan wins. Since Zhaorun can only decrease the value so that A is not equal to B, and I should add the hypothesis here. So A is not equal to B. Since A is not equal to B, this is the winning state for Xuan, as we have also seen here. This is the winning state for Xuan, so he will always win. And this proves that this problem. So when A is not equal to B and at least one of A and B is larger than or equal to 2, Xuan will win. So these are all the starting values A and B for which Xuan will win the game. So that is for this problem. Do you have any question for this one? Okay, so let's take a look at the next problem. So, and also for this question, for problem 2, let me add another point. This is actually let me see, how do I write this? Zhaorun Lin. You can Google that. This is a special type of Zhaorun Lin. Yeah. And problem 3. So we're adding on top of problem 2 some additional rules. So in problem 2, we can only decrease one value by a non-natural number. But in this problem, we can actually decrease both numbers by the same non-zero natural number. So when the state is in 10.6, we can decrease it to 8.4. We can decrease both of A and B by 2. So this is an additional rule for this problem. And also when in this problem, a player who cannot move in this game will lose the game. So it's different. And also as before, let's for problem 1, let's take a look. So also you can also prove that easily as we proved in problem 2, A and B must decrease, since we are always decreasing by both or one value by a non-zero natural number. So the game states are also deterministic. There is only one winner. So the properties are actually the same as in problem 2. So let me also write some cases for this problem. So for game state of 0, 0, the winner is Zhaorun. Since in this case I cannot move, then because Xuan is starting first, since he cannot move, so he loses the game and I'll win the game. So for 0, 1, for 0, 1, Xuan can only decrease the value of B, then I cannot move, so Xuan will win. And you can generalize it. For any other value of B, Xuan can always decrease it to 0, and then I cannot win. So Xuan wins in all of these cases. And for what about 1B? 1B. Xuan can decrease the value of B to 1. So if he decreases B to 1, then I am only forced to decrease the value, one of the value to 0. Then he can decrease another value to 0, and I cannot move. So Xuan will win. Actually, there's another easy way of doing this. Since for 1, 1, we can just decrease both A and B by 1. So I can only Xuan will always win. Since we have another rule that we can decrease both numbers by the same non-zero natural number. So actually, by this you can easily see that for 2, 2, Xuan can decrease both value by 2, so Xuan wins. And also 3, 3, Xuan wins. So when A and B are equal, Xuan wins. And we can easily deduce that since with this constraint, A and B must be smaller than or equal to 10, the largest position, A and B, for which Xuan will win is just 10, 10. So Xuan can decrease both value by 10 and win. So this is easy for part 1 of part 1 is easy. And for part 2, we'll have to write up all those cases again, since it's a little bit difficult to deduce the winning position for Zhaorun. So let's write for 0, 0, I'll win. 0, 1, Xuan wins. 1, 1, Xuan will win. Since as we explained before. And 2, 0, Xuan will always win. Can decrease 2 by 2, so it's 0, 0. So you can see that Xuan will always try to decrease the states to another state for which I will win. Since in this state, originally Xuan is starting and it ended up with me winning. So when Xuan decreases some game state to this game state, it actually switch the winner. So if Xuan decreases to 0, 0, in this case I am starting, so you ended up with him with Xuan winning. So for any A and B higher than for any other A and B, the game states that are larger than the game states A prime and B prime, then we can always try to decrease it to another game state in which the opponents will win, then I will win. So for 2-1, let's see if Xuran can decrease it to 0-0. It's obvious that we cannot do this by one step. So we can either decrease 2 by 1 or 2 by 2, and both of them by 1. But in all of the cases, we cannot reduce it to here. So in this case, I will win. And in 2-2, it's obvious that Xuran can decrease both value by 2. So we already found one position in which Zhaorun wins. Let's do 3-3. Let's do 3-0. 3-0, obviously Xuran wins. 3-1. 3-1. Xuran will also win. Actually 3-2 and 3-3. Xuran will win. So it's very easy to check. You can check that. So you can deduce it all the way down. 4-0, we're just trying to decrease the game state to another game state in which I will win. In that case, Xuran will in this game state. Otherwise, I will win in this game state. So you can decrease, you can deduce all of the possible A and B value. It'll be very quick. And in the end, you will find that actually the largest starting position, it's 7-5 for Zhaorun to win. So yeah, for this problem, it's just very tedious. You can just write down all the possible values, and actually there are only a few game states in which Zhaorun will win. So you can easily find that this is the winning state for Zhaorun. Do you have any question for this part? Okay, so let's go to the next left, the only problem left that are not covered in the lecture. So we are trying to prove this. I will first prove that n factorial is smaller than or equal to 2 to the power of n log n. And then I'll prove it in another way that 2 to the power of n over 2 log n minus 1. It's smaller than or equal to n factorial. So if I prove in these two parts, then I essentially prove this equation. So let's write it down for this. You can just take a log, take a log of both sides. So take a log minus 1 minus 2 to 1. So, and in this side, we take a log of base 2, so it becomes this. V. And we can write this part as I equal to 1, and we add it up to n. Right, since this part is equal to 2 plus log 2 and minus 1 all the way to log 2, 1. So we can just add them all up. So um, we can easily see that for this part, it is smaller than must be smaller than or equal to this, to n, which is n log n, and they're the same. So we prove that it must be smaller than or equal to the right hand side. So this proves this part. And for the next part, just for the next part, we can also take the log of both sides. But before that, let me do before that. Since we are asking for when n is an even number, so we can write n as this. So n factorial is 1 to 1, which is 1 times n, 2 times n minus 1, 3 times n minus 2, all the way to 2 over n times n over 2 times n over 2 plus 1. So this is, so if you think this is strictly, no, this is larger than or equal to this one, right? Since this part is it's larger than or equal to, no, actually. Since each of these parts are larger than or equal to this, right? Since n is an even number, so we can see that it is larger than or equal to this part. And for this part, if we take, if we just expand it, it becomes this, and then times, yeah. So we can write it as, can write n factorial as this, and then let me substitute it to the equation. N times 2, and then actually let me first take a log of both sides. Yeah, since log of n factorial is greater than or equal to log n. So this part is the log of this. Is the log of this part. If we take log 2, it will become, so log n, and then minus n over 2, right? So if we take a log of both sides, it leads to this equation. And then we can see that it's 2. And if we just get rid of the log, it becomes this part, and which is exactly this. So this proves the greater than or equal to part. So at the end, we will prove this equation, this inequality. Yeah. Do you have any question for this part? Okay. So for problem 1, it's actually taught in the lecture. So I'll just give you the answer, but it's also in the lecture. So for xn, we have in the lecture we have seen that it is actually equal to n minus 1 times xn minus 1 plus xn minus 2. So this is the this is the equation for xn. So I'll just give you the program, since this program is easy, so it's very short program. So I'll write it with my hand. So let's first initialize the variable of the variable of x0 and x1. Also, let me mention that x0, it means that we have to derange 0%. So how many ways we can derange 0%? So there is only one way. So x0 is 1. And then how many ways can we derange one student? So it is 0. So we cannot derange one student, since he must sit in some place. So he must sit in his own seat. So x0 is 1, so and x1 is 0. So we'll just first initialize maybe 2 variable. Let's call it x minus 2. X minus 2, I'll initialize it to 1. So which is x0. X minus 1, it's 0, which is x1. So then in a for loop, we can complete the calculation. So we just for I in range from 2, since since 1 and 0 is already calculated. So from 2 to 83. We want to find 82, so we have to go to 83. So, or maybe just 82, since it's just a pseudocode. 82. Then we will calculate that xn should be I minus 1. So I minus 1 means that, for example, when n is 2, I is 2. So we want to calculate this n minus 1. So we use I minus 1. So I minus 1 times xn minus 1 and xn minus 2. Actually, let me just write these 2 variables as n minus 2 and n minus 1. So xn minus 1 plus xn minus 2. This is xn. And then after we calculated xn, we can just substitute. So now if we want to move to next step, n plus 1, the n minus 2 actually becomes the xn minus 1 now. So I'll assign xn minus 1 to xn minus 2. And then xn minus 1 will become the xn now. Xn calculated here. And then just need to go to the for loop will loop again, and then eventually we'll find x82. Also, maybe you should also initialize x outside of the for loop. So yeah, this is the code, and in the end, you just need to print x in so you can calculate the value of x82. So this is the program for finding x82. Yeah. Do you have any question for this part? Question one. Okay, so if not, yeah, that'll be all for today's tutorial.